You know when you're watching a chemical reaction, maybe in a beaker, and you see the bubbling stop, the color settles, and you think, okay, that's it, it's done. Well, what if I told you that in a lot of cases, the moment it looks completely still is actually when the most frantic, nonstop action is really happening? Let's dive into this amazing illusion of stillness and uncover the buzzing world of dynamic equilibrium.
So here's the deal. On one hand, you have what our eyes can see, the macroscopic view. The mixture's color, its composition, it all looks perfectly constant. You'd swear the reaction is finished. But if we could zoom in, way, way down to the microscopic level, we'd see a totally different reality. At the atomic level, molecules are in this constant, furious dance, swapping atoms and reacting at an incredible speed. The system hasn't stopped at all. It's just achieved a state of perfect invisible balance. So, how is that even possible? I mean, how can you have all this constant motion and yet see no overall change? It kind of feels like a paradox, right? But the answer is really cool. It lies in a perfect balancing act, like a cosmic tug of war between two opposing forces.
And this slide gives us the perfect analogy for it. Just think of a scale. On one side, you have your starting ingredients, your reactants, A and B. They combine to make the products in what we call the forward reaction. Now, as they get used up, that reaction naturally slows down. But as the products, C and D, start to pile up, they begin to react with each other and break back down into the original reactants. We call that the reverse reaction. And it gets faster and faster as more products are made. And this brings us to the most crucial point. The equilibrium state is that magic moment when the speed of the forward reaction exactly matches the speed of the reverse reaction. Reactants are turning into products at the very same rate that products are turning back into reactants, and the result, the overall amounts, the concentrations of everything in that beaker just lock right into place. And you can actually see this beautifully in the data. This graph here shows the concentration of our reactants, that's the blue line, going down over time. Makes sense. At the same time, the concentration of our products, the orange line, is going up. But look what happens right at that dotted line. Both of those curves just flatten out. That is the signature of equilibrium. The flat lines tell us the concentrations aren't changing anymore. And notice, they don't have to be equal, they just have to be constant.
Okay, I know. Graphs and molecules can feel a bit abstract. So to make this concept really click, let's ground it in a real-world analogy that anyone can picture. Imagine you've got two big glass cylinders. You start scooping water from the first one into the second, and at the exact same time, a friend starts scooping water from the second one back into the first. At the beginning, yeah, the water levels are going to change, but eventually you'll get to a point where the amount of water you're adding to each cylinder is perfectly balanced by the amount being taken out. The water itself is still moving back and forth, but the water levels in the cylinders become totally constant. That's dynamic equilibrium, right there. So let's just translate that directly back to our chemical reaction to make it super clear. The water level in each of those cylinders, well, that's like the concentration of our reactants and products. The act of scooping water back and forth, that's our forward and reverse reaction rates. And those constant, unchanging water levels, that's the state of equilibrium itself, dynamic and super active, even when it looks totally static. Now, let's see how this plays out in the real world, because this is not just some neat theory in a textbook. It is the foundation of massive industrial processes. Take the Haber process, for example. It's used to make ammonia for fertilizer that, literally helps feed billions of people. At super high temperatures and pressures, nitrogen and hydrogen react to form ammonia, and they reach a dynamic equilibrium where the composition becomes locked, even while those forward and reverse reactions are just churning away. But, all this talk about invisible motion brings up a really important question. It's exactly the question a true skeptic would ask, and honestly, it's a brilliant one. I mean, seriously, if everything looks constant, how can we be so sure that all that activity hasn't just stopped? It's a totally fair point. For all we can see with our own eyes, maybe the reactions just ran for a bit and then stopped cold. How could you ever prove that wasn't the case? Well, scientists came up with an incredibly clever experiment using something called an isotopic tracer. They set up two identical experiments to make ammonia. The first one used just normal, everyday hydrogen. But the second one used deuterium, which is just a heavy isotope of hydrogen. You can think of it like hydrogen with a tiny little tag on it. And they let both reactions run until they reach their own separate but identical equilibrium states. And then they did something so simple but so profound. They just mixed the two containers together. Now, if the skeptic was right, if the reactions had truly stopped, then all the original molecules would just bounce around, coexisting forever, totally unchanged. But that's not what they found. They took the new mixture and analyzed it with a machine called a mass spectrometer, which can identify different molecules based on their weight.
And here it is, the smoking gun. The mass spectrometer found all sorts of new, scrambled molecules. It found ammonia with both regular hydrogen and the heavy deuterium attached. It even found hydrogen molecules made of one of each type. Now, these new molecules could only have been formed if the chemical bonds in the original molecules were actively breaking and reforming. The atoms were continuously scrambling themselves.
This was the ultimate proof. The verdict was in. Equilibrium is not a state of rest. It is a state of relentless, continuous activity. There's no net change that you can see, but there's infinite change happening down there at the molecular level.
So the proof is in the pudding. We know this hidden activity is totally real. So now, let's just lock in our understanding by summarizing the core principles that govern this perfect, dynamic balance. Here's a fascinating property of equilibrium. It is completely direction agnostic. It just doesn't matter if you start on the left with 100% pure reactants, or if you start all the way on the right with 100% pure product. As long as your conditions stay the same, the system is going to relentlessly drive towards the exact same final mixture, the exact same balance point. So the crucial points to take away from all this are these three principles. First, the equality of rates. The forward reaction speed perfectly matches the reverse reaction speed. Second, the constancy of composition. Because those rates are equal, the measurable amounts of everything just freeze in place. And third, unceasing activity. Beneath that calm surface, molecular bonds are breaking and forming infinitely. The system never, ever truly stops. So, the next time you see a reaction that looks like it's finished, just remember this. You're not looking at an endpoint. You are witnessing the architecture of perfect balance. It is not a state of rest, but a state of perfect, continuous, and dynamic compensation. A hidden molecular dance that never, ever ends. It makes you wonder, what other quiet surfaces in our world are hiding this kind of relentless activity?